Hi, everybody. Welcome to the first lesson of Unit 7, Math 1B, called Introduction to Geometry. The goals for this lesson are to learn the Greek origins of geometry, understand the first 8 geometric axioms, and learn some careers that utilize geometry. These 3 topics will be on the mastery test. A reminder, after this lesson is over, you should be ready to take the first mastery test in Inventum, Unit 7, called Intro to Geometry. And you must also take notes on this lesson, this video, and send them to Josiah for attendance participation credits. So either upload it into Google Classroom or send it to me as an email, some pictures of your notes. So these 2 things are your assignment for today. Notes on the lesson and take the mastery test. So, geometry is an ancient Greek word, or at least it comes from the ancient Greek. Geo, that means earth. And met is measure. So this literally means measuring the earth, and then or the study of measuring the earth. So that's what geometry means. Of course, we'll use it to measure lots of different things. Other ancient cultures besides the Greeks used geometric ideas and principles completely independent of the Greeks, including in ancient China and India and Egypt and other places too. However, the ancient Greeks get credit for being the first to do geometry in a formal, systematic, logical way. And that's why we give them credit and focus on their style and how they started doing geometry, because it is this formal, systematic, logical way. This is important. Around 300 BC, and for context, that is about 2,322 years ago from now. So 2,300 years ago, an ancient Greek named Euclid, say it out loud at home, Euclid, wrote / compiled his book called The Elements. Here's one artist's interpretation of what Euclid might have looked like based on some descriptions. And here is an idea of an early version of The Elements, the book. Both of these paintings and book covers we're looking at are from the 1500s, not 300 BC. So like the Middle Ages, the time of kings and queens and stuff like that. But this book was written very early, 300 years before the Common Era, 2,300 years ago, roughly. So what is so special about Euclid and his book, The Elements? The book, The Elements, approaches geometry in, like I said earlier, a systematic and logical way. What do we mean by that? It means that it uses what's called undefined terms, axioms, definitions, and theorems to start from the very basics, like points, lines, and planes, and builds up or proves more complicated rules. Next, we're going to dig into undefined terms, and then axioms, and definitions and theorems to see what we mean by these. So the undefined terms. What does this mean? These are the basic ideas, the very beginning building blocks of geometry: points, lines, and planes, upon which all other definitions that we will see or use are built. So this is like the very beginning or foundation, the undefined terms: points, lines, and then planes. Flat spaces is what a plane is. We'll look at that more in a second. An axiom. This is using undefined terms to create a statement. And here's an example. Given any 2 points, A and B, there is exactly one line, AB, passing through them. So this is an axiom because it's more complicated than just using 2 points, right? It's not just saying points A and B exist. It's saying what can we then learn from if we have 2 points that exist? Is there more than one straight line that passes through both of those? No. If we try to make 2 or more lines, straight lines only, mind you, that pass through AB, it doesn't work. This one is not passing through both. If we make one that passes through both, okay, there's one line that goes through AB. However, can we make another straight line that goes through both A and B? No. And that's where this axiom is coming from. It's something that like follows logically from the existence of 2 building blocks, 2 points. There's many more axioms that involve using lines or planes or other figures too. And this is just one example. So an axiom is kind of like one step up from an undefined term because it uses those. Definitions are next. Definitions just think of as a formal way to express the meaning of a term or idea. So this is kind of like including undefined terms, and later when we get to other things like a circle or a sphere. Now theorems. Think of theorems as the next step up after axioms. These are a statement that is proven to be true using undefined terms, axioms, or definitions. More specifically, a theorem is going to be using many different axioms put together. So it's going to be, for instance, assume statement A is true. And also, if we had information that said if A is true, then B is true. Well, then, we could also say logically from this, B is true. Because A leads to B. And if we can assume A is true, that means B must be true also. So this is a generic version of a theorem linking together earlier true statements. So if this is true and this is true, then it yields B being true at the end. And this is a good example of the logical systematic way that we do geometry based on the Greek method laid out in Euclid's book, The Elements. So it's linking together logical chains of ideas. If one thing is true, then it leads to another, which leads to another, which leads to another, getting more and more complex, starting from earlier, simpler building blocks like just points, lines, and planes. Now, I really quickly want to define with you the undefined terms. And this is a little weird because I know that we're calling them undefined terms, but points, lines, and planes, they're called undefined because they're foundational, because they're basic, and because we can only really describe them or define them based on an example. So a point is a one-dimensional object. It's just a dot, like point A, for example. It doesn't go in two directions. It only has one little point that makes it up. A line, though, in our geometry, will only be working with straight lines for now. So when I say line, or when you read line in your Inventum or text in Inventum, they only are referring to straight lines like this. A line is composed of at 2 points. So any 2 points, let's try that. Let's just make a point right here, and then randomly anywhere on your page, make a second point, call it B. Any 2 points you create or find, there exists one line between them. So you can think of a line as the connection between any 2 points. Straight figure in between two points. And then a plane. What the heck is a plane? So a plane is simply adding in a third point. So this you can think of as the space in between 3 points. This is not a formal definition, but this is kind of a description, a space in between 3 points. So let's kind of play with that and see what that looks like. I make a random point A. We make another one B. We already see that we can have a straight line going through that. What if there's a third point, C? So yes, this creates a triangle, but if we're not concerned with the space only strictly in between them, like for instance, I draw my line AB, and what if we connected all three? So A goes to C, and B goes to C, and that's not straight, but pretend it is with me, please. Now we're talking about all the flat space generated in between all of these lines, not just in the middle. So not just in the middle where the triangle is, but what about out here? That's some flat space that's in between this section and this section. And then between this area here and this area here, it's all the same flat space. So look around you in your room or wherever you're doing this lesson right now. You have probably a lot of different examples of flat spaces. One is your computer screen. It is a flat space like a page, right? Your walls are also a plane. The floor beneath you is a flat two-dimensional space like a plane. It takes a minimum of 3 points to make a plane. I'm going to come back to this presentation, but I want to show you real quick. Last semester, we used GeoGebra a lot. This is geogebra.org/3D. Feel free to use this as a tool while we're doing this unit or others in the future. It's built a little differently than the GeoGebra we're used to, but it has a lot of the same tools. So geogebra.org/3D. So if you type that into your computer, and if you click on the screen in the middle there, and click and pull and rotate, what do we see? We've got what looks kind of like a graph, like what we're used to, with a y-axis going up and down, and depending on how you rotate it, you can see an x-axis going left and right. So my blue line is kind of like y. The green line here is our x-axis. So what the heck is that third line, the red one? Well, that is another axis coming out straight towards us. And if you rotate it, you can see it. This is a third dimension. So the you can think of the y as the first dimension, the x as the second dimension, and when we only have x and y, like what we're used to, right, for our functions, that's two-dimensional. We're just looking at up, down, and left, right. Those are the two dimensions. Once you throw a third direction in there, which is like forward and backward, that's the red line creating a 3D space. Um, if we're using GeoGebra to play around with these ideas, we see already that gray square, right, that I'm kind of moving around in the screen. That is a plane, a flat surface. If you look at it straight down the middle, it looks like a line. But if we look at it from an upper perspective or a lower perspective, you can see that it's like a infinite flat space. We can make another one here to demonstrate 3 points make a plane. So I'm going to do that really quick. If we go to tools on the left side, we get some beginning tools. And if you click more, there's, all the stuff you might remember from regular Inventum. I'm going to click less again. Okay, so using just the 3D tools at the top, I'm going to make 3 points really quick. So I'm going to make one here on our blue line at 4. And let's make one at, we'll use all the 4s. Why not? We'll put one at 4 on the red line. And I'm going to rotate a little bit to see my green 4. And I'll put one there. So I've just made a point A, B, and C. Point A, B, point A, point B, and point C at all the positive 4s. Just to play around with it. And now I want to try making a new plane through those new points I just created. And this says select 3 points. So I'm just going to click on A, then B, and then C. And I'm going to rotate this now. You see the new plane it created is kind of light blue colored. It's another flat surface. So we've got our original plane that it kind of came with, the gray one, and then we have our new bluish one cutting through it. So think of planes as kind of like pieces of paper or flat walls, maybe. Now, the plane itself is actually just two-dimensional, like your surface on your screen or your window or your wall or your floor, or like this blue plane I just made here. The entire graph, though, using the green, red, and blue lines, it's all together 3 dimensions. So please feel free to use GeoGebra/3D, geogebra.org/3D, to play around with these concepts on your own too. Okay. Now, next up, what we're going to look at is one of our goals for today, and that is to examine the first 8 axioms. It's this goal here. I want to examine and understand these first 8 geometric axioms. So these are straight out of Euclid's Elements, the book that I referenced earlier. And there's plenty more axioms, and there's lots and lots of theorems, and we'll look at some of these things throughout the rest of the semester. But I want to expose you all to the first 8, do a quick little example for each one maybe, and have these in your notes to refer back to. So, number 1, given any 2 points A and B, there is exactly one line AB passing through them. And we did this one earlier. So given any 2 points A and B, what this is saying is assume or let there exist these 2 objects, point A, point B. There is exactly one line called AB that passes through them. You can't make more than one. You can't make less than one. There is exactly one line that goes through your 2 points, no matter where they live. Okay, number 2. This one is subtitled The Distance Postulate. This may come up in your mastery test. Make sure this is in your notes. For any two distinct points, there exists a unique positive number called the distance between the 2 points. For any two distinct points. So again, we have A, we have B. I've randomly made these. However, there is a number, a measurable number called the distance between A and B. Just like if I made let's say we have more different unique points. Let's say we have points M and J right here. Well, these distinct points have their own distance in between M and J. Maybe it's the same as AB, maybe it's different, but they have their own distances, their own links that are unique and belong to them. You might think this is a little overthinking, and honestly it is. It's overthinking and it's overanalyzing some things that we probably take for granted. Distance of MJ, and this is distance of AB. Now the next two postulates are going to also have to do with this space between 2 points. The first one is called the ruler postulate. This is number 3, the ruler postulate. Here we go. The set of points on any line are in one-to-one correspondence with the set of real numbers such that the distance between a pair of points is identified as the absolute value of the difference of the corresponding real numbers. Folks, I thought about rewording this to make it a little easier sounding, but then I changed my mind and decided I'm going to do the original whole version of it with you. But let's try to see what the point is of this number 3 ruler postulate. The set of points on any line are in a one-to-one correspondence with the set of real numbers. So what this is saying is between any 2 points, we can measure them. So it's like taking the second axiom, number 2, that says there exists a distance, and it's basically saying that we can measure that distance. It's not just unique to A and B, but also it's measurable. So you can take your ruler, and we could find A and B where they live on that ruler on any line, as it mentions in it, and find the actual distance or the actual measure between them by doing this at the end, the absolute value of the difference. So let me start this example over again really quick. So please do this with me in your notes. So let's say we have a line and it has a ruler on it, like so. Now, this business about one-to-one correspondence, this just means that a ruler is set up in an ordered one-to-one way, meaning all the units are the same amount apart. So assume our ruler is here on the screen. The space between 0 and 1 is the same as 1 to 2 and all the rest. That's what they mean by one-to-one correspondence. Now, the 2 points live right here. There's A. And let's say B is right here. Okay, I purposely didn't put A on a whole number. That is halfway between 0 and 1. So A lives at 0.5. B lives at 4. Now, there's many ways to look at this and try to find the distance between A and B. What the ruler postulate is saying is that one way that always works is to take the absolute value of the difference of the corresponding real numbers. So let me show you what they mean by that in purple. So what are the corresponding real numbers of these 2 points, A and B? Well, one of them is 4. We see that, right? And the other is 0.5. We see that. So let's take the difference and then the absolute value of these 2 numbers. So 4 minus 0.5. What is that? Try that on your own. 3.5, right? Now take the absolute value. What's the absolute value of 3.5? Remember, absolute value gives you only the positive of whatever's inside. So it is 3.5. What the ruler postulate is saying is that no matter where your points live on the number line, being a one-to-one compared to each other, you can take the difference, you can take the absolute value of that, and find the length between the 2 points, 3.5. And for instance, why is the absolute value being used? Well, what if we took the difference the other direction? Meaning I did 4 minus a half. What if we did instead 0.5 minus 4? What does that give you? Try that on your own. Try your calculator if you need to. If you do 0.5 minus 4, you get negative 3.5. Let me ask you, can distances, measurements of things, of space between you and me in a classroom, can that be negative? Of course not. Excuse me, distances are always positive. That's why we're doing the absolute value. So if I take the absolute value of this negative 3.5, that of course gives us 3.5 units. The point is, the absolute value always gives you a positive number. The bigger point here, folks, is the ruler postulate is just saying that the space between any 2 points that exist can be measured. I realize that this is really wordy and probably kind of scary and confusing. The main takeaway is that any 2 points can be measured, the space in between them, using your ruler of whatever size that is, as long as it's 1-to-1 spaced apart. Okay, number 4, the ruler placement postulate. Now this one's a little weird. Let's read it. Given any 2 points, A and B, on a line, a coordinate system can be chosen in such a way that the coordinate of A is 0 and the coordinate of B is positive. So think of number 4 as a branching off and a kind of a more precise version of number 3. This is saying instead of having A and B exist on some weird space like my last example, 0, 5, and 4, right? This is saying, well, we have the freedom to slide our coordinate system, choose it in such a way so that we slide A to be 0, and that would make B 3.5 because we just measured it from our last example. So if we were to be able to take our ruler that these guys down here live on and slide it, I guess this way, we're choosing our coordinate system differently to make that measurement easier. So instead of having A be at 0.5, I'm sliding it and making my A at 0. And we know it's 3.5 away, so that means the B would be at 3.5 now. Next up, number 5. Okay, 5 is our last a big one, just so you know. Okay, so 6, 7, and 8 will be a little faster, a little easier. Number 5, every plane contains at least 3 points that do not lie on the same line. Every plane contains at least 3 points that do not lie on the same line. So earlier I talked about how we need 3 points to make a plane. If you just have two, all you have is a line. As soon as you introduce the third one, then they form together that flat space that we call a plane. Of course, there's more than just 3 points in a plane. Once you define it, you actually have like an infinite number of points living in it. Like, for instance, this one, assuming that is in between all those lines, right? This new point D is a fourth point that lives in it. And what about E? He also lives in it, and G. So there's an infinite number of points in your plane, but this is saying that you must have at least three. And notice that my original three, A, B, and C, do not lie on the same line. If you choose 3 points that do lie on the same line, I'm going to call this X, A, B, and X. These are all purposefully on the same line. Well, there's actually an infinite number of planes going through this, not just a single plane. You must have X be off of it, like C is over here. C is not on the same line. And it creates a unique single plane. If you have 3 points on a single line, there's an infinite number of planes going through it. An example of this is if you take a book and all the pages are meeting at the binding. So you can think of all the different flat pages going through. Let me try to draw a picture of this quick. Here's a line. We have a plane here going through. But there's also another one at kind of an angle going through. And another one in between them. So I hope you see the pages kind of emerging here. And maybe one going straight left and right like the x-axis. I'll try to draw that. And on the other side, there it is. So we have all these pages, all these planes going through this single line that we started with. That's the problem with having the 3 points on the same line. Okay, there's a second part to this. There are at least 4 points in space that do not lie on the same plane. So now they're saying 4 points. What's important about that? If we have our plane defined like A, B, C over here, plane A, B, C, well, what if we have a fourth point that's not on it? It's saying, this axiom is saying that there are at least 4 points in outer space, in three-dimensional space, that once you throw that fourth one in, it's like not going to be on the same plane. 3 of them will be, but that fourth one is not. The point of this axiom is that it is distinguishing between lines, one-dimensional, planes, two-dimensional, and then space, three-dimensional. So that's kind of the main takeaway here. But it also is important because it is kind of setting in stone that you must have 3 points to make a plane. And then there exists at least one fourth point off of that plane. Let me show you a picture of this on GeoGebra real quick. So here we have our 2 planes, right? We have our original gray one, and I'm thinking of that as like our flat one. And then we made our new blue one going diagonally downwards. See that? Now, already, I hope you see the 3 points that are making up our blue plane, A, B, and C. So there's 3 points that we use to create a plane. Of course, there's many others. Like, I could make a new point on it. Let's see if I can show that. So I want to make a point on my plane right there. And then back out and look at it. So I made point D. That's a fourth point, but it's on my plane, right? And I'm doing this to show you that there's an infinite number. You could keep making points on the blue plane. Boom, boom, boom. There's no stopping it. There's an infinite number. Now, what about the fourth point business that the axiom mentioned? So going back to just the original plane, the blue one, okay, just points A, B, and C, it's saying that there exists a fourth point that doesn't necessarily have to live on the plane. So what about if I picked right here for point D? So here's point D, kind of floating in space on its own. He's happy. He doesn't care about the blue plane. He is a fourth point that exists that is not on the defined plane that we made already. That's the point of axiom 5. Okay, we're almost done with the axioms, and then we'll look at some careers that utilize geometry. So number 6, if 2 points lie on a plane, then the line containing those points also lies on the plane. If 2 points lie on a plane, then the line containing those points also lies on the plane. So I'm going to try to draw a diagonal plane for us. So here's a flat space, and I've got 2 points, A and B, on it, on my flat page here. The line containing those 2 points, so we draw a line through AB. This is saying that the line AB I just created has to be on the flat space, on that page. It's not going off through it in a different direction. So here's our blue plane. Let's make a line through AB. Line through A and B. Okay. Oops. Okay, so there's my black line I just made going through AB. I hope you can see that. And the point is, it's a straight line and it lives on the blue plane. Because A and B live on the plane, it stands to reason that our black line cannot go veering off sideways. It's not going to go shooting through at a single point. It's cutting across the entire blue plane forever. That's axiom 6. Again, you might be thinking something like this rule might make sense to you to the point where it doesn't need to be stated. But that's honestly the point of geometry, is that we are stating everything and showing how it must be true and not just assuming it. The only things we do allow ourselves to assume are these undefined terms back here. These are what we're assuming. Points exist, straight lines exist between points, and planes exist between 2 different lines or 3 points like this. That's what we can assume. The rest we have to prove it from this, basically. All right, number 7 and 8, we're almost done. Hang in there and keep taking your notes. I want to see pictures of all this sent to me, please. Number 7, any 3 points lie on one or more planes. Any 3 points lie on one or more planes. Any 3 points not on the same line can lie only on one plane. And we've talked about this already, I think. So we don't need to do it again. Any 3 points not on the same line can only lie on a single plane, not more than one. Lastly, number 8, the intersection of 2 planes, if it exists, is a line. So the intersection of 2 planes, if it exists. So what if it doesn't exist? Well, an example of this would be holding 2 books in front of you. Let the books be the planes, even though they're thicker, so it's not a flat space, but maybe just the top of one book and the top of the other. Let those be your planes. If you hold 2 books in front of you, perfectly horizontal or parallel to each other, here's the top of one book, and then below it, we've got the top of our other book. assume we can hold these nicely parallel. Well, these aren't going to intersect. So because they're parallel, there's no intersection here. But if they aren't parallel, like maybe two pages, you can make, point them towards each other diagonally, like this. Let's try to draw that. Here's one plane, and then we have another one going in a different direction. Well, the intersection of those two planes is a line right here, a straight line. The intersection of two planes is a line. Again, I want to just try this on GeoGebra. And for instance, see our blue plane that we've been using and see the gray plane that it came with at the beginning. Well, you can see where my mouse is, where they're intersecting. The blue one is like cutting into or crossing through the gray zone below. Let's see that line. I'm going to connect C to B. And now we see the line that the let me erase this one here. Okay, so I connected C to B, and that is the line that is the intersection of the blue plane and the gray plane. So when two planes cross or intersect, they're intersecting in a single line, CB in this case. That's it for the axioms. We went through the 8 axioms. I think some of them are a little easier to understand than others. I think number 1 is okay, maybe even number 2. I understand that things get a little crazy with number 3, 4, and 5. And then number 6, 7, and 8 are shorter and might make a little more sense. So do your best to make sure that those are in your notes with examples if that's helpful for you. Last up, I want to just go through some different careers with you that use geometry. Now, here's what I want to say about notes. I would like you to at least write down what I've put in bold, the names of the different jobs. So, aeronautic engineers, and frankly, guys, engineers of all types use geometry in some way. Aeronautic engineers use geometry to design aircraft. So, I'm going to have a lot of different jobs and careers on the page soon. And all I want you to at least list off in your notes are the bold types of jobs. Okay, you don't have to write, don't have to take notes on the rest of it. So I'll underline it as well. What I want you to have: air traffic controllers use geometry principles to chart flight paths. Pilots use geometry to navigate. Astronomers use geometry to measure lots of things, to measure the sizes and the distance between celestial objects. That means planets or stars, the speeds and directions of their motions, and the orbits that they trace. So, astronomers use geometry in lots of ways. Architects use geometry, and again, engineers, civil engineers use geometry to design their layouts of buildings and landscapes. Interior designers use geometry, and other designers who use computer aided technology. Fashion and jewelry designers, doesn't even seem like a mathy thing, right? But they totally use geometry also. And then other types of artists, like sculptors and painters of all different types, of different types of sculpture, totally use geometry, and photographers as well. And then some medical industry ideas: medical imaging technologists. These are like the people who do your MRIs. They use geometry to generate pictures or just to interpret the pictures. They have to really have an idea of geometry to just understand what they're looking at and to explain it to like you and me when we go into the doctor. Medical researchers, and then physiotherapists too. So here's just some ideas of different types of jobs that will use geometry ideas in their practice. That's it for today's lesson. You might notice we didn't do any real math, right? There's no problems that we solved, but it is very conceptual using the axioms. Again, send me a picture of your notes for this to count for credit for you to be participating and attending class today. That's your attendance. Also, as always, you're expected to do your mastery test. It's called Intro to Geometry. It's the first one in Unit 7. What's in the mastery test? There's going to be, frankly, everything I gave you could be in the mastery test. All three of these here. The stuff I went over about the Greek origins, so Euclid, his book, The Elements, the basic idea of why he's important, that's all in there. There's some questions about the first 8 geometric axioms. These could be in the mastery test. And then there's a couple questions that ask about the careers. So that's what you should have in your notes. That's what you should be ready for in the mastery test. Have a terrific day. Thank you for participating.